Okay, so I'm going to draw a ladder to start with here. Okay, and the problems are this lesson are different from the others in that they're called double pivot problems. So there is Albert applying a force up, and there is Brian applying a force up. So we're going to call those FA and FB. Okay, and the difference too this time is that the ladder is a symmetrical object resting on the shoulders of Albert and Brian, and the ladder has its own weight force, and that acts through the center of the ladder. So that is there, and we are told that that is 1200 newtons, so we can write that in. Okay, now I've also talked before about force up equals force down, and today we need to take that into account. So our forces upwards are the force of Albert and Brian, and that's got to equal 1200 because there's only one weight force acting down. There's nothing sitting on the ladder. So the upward force of Albert and Brian equals the downward weight force of the ladder. So we'll come back to that a little bit later. That's probably the easiest idea so far. And the other thing I should remind you is that that weight force is acting 4 meters in from Albert and 4 meters in from the other end of the ladder. It acts through the center. Okay. Now, if Albert, so that's that first part. I'm going to draw the same thing again down here because I want to show you something else before we actually get into the question. Here's FA. Sorry, FA and FB here. Now the next thing I want to do is, because we've got two people holding up the ladder, there's potentially 2 pivot points. Okay, so if we take this point here as the pivot point, okay, if Brian wasn't there, the ladder would fall in this direction. So the ladder would turn in a clockwise direction if Brian wasn't there. So that's the clockwise torque, of the ladder. Okay, would come around like this. Now, it's what's stopping it coming around like this is the force that Brian is applying upwards. And if Brian just kept pushing and pushing and pushing upwards, what would happen is he would make the ladder do that. So that is the anti-clockwise torque provided by Brian. Provided by Brian. Now the really important thing to understand, okay, is that potentially if the pivot point wasn't here, it could be here, in which case the ladder would fall in an anti-clockwise direction, okay, and Albert would be providing the anti-clockwise torque. So there are 2 possibilities, and it's really important to get your head around which one of those we need. And in this case it's this one. So I'm just going to turn the page and start the problem properly here. So we've got an 8 meter long ladder, and we've got a weight force acting through the center of 1200 newtons. Now we've got an upward force at the end here, which is the force that Albert's providing, and he's right on the end of the ladder. Okay, however, Brian is 2 meters from the end of the ladder. Okay, and part A says calculate the clockwise torque exerted by the weight of the ladder about Albert's shoulder. So I'm just going to write in these torques again. So this is going around this way. Would be the clockwise torque of the ladder, and here is the anti-clockwise torque provided by Brian. Now the reason I know that I have to use those two is that it says calculate the clockwise torque about Albert's shoulder, and about Albert's shoulder is your clue that Albert's shoulders become the pivot point. Okay, so Albert's shoulders become the pivot point, and so we're going to make this point here the pivot point. So we're going to measure everything from there, and so from the pivot point to the weight force of the ladder would be 4 meters, and Brian would be standing 6 meters away from Albert. Okay, now that's kind of important. The next thing that we need to do is we need the clockwise torque. So for A, the clockwise torque is the weight force times the distance. So this is the clockwise torque exerted by the ladder. Okay, so for the ladder to be coming in a clockwise direction, it's got to be coming around like this. So that's why we know we have to pin it there, because that's the only way we're going to get the ladder coming in a clockwise direction. And so it's weight force, which is 1200, times distance, which is 4. So that's 4,800 Newton meters is the clockwise torque provided by the ladder. Then part B says, by taking torques about Albert's shoulder, find the force that Brian exerts upward on the ladder. So this is where we need to make the clockwise torque equal the anti-clockwise torque. So this torque coming around here has to equal that one to keep the ladder in the horizontal position. So we've got 4,800 equals the force that Brian is exerting times the distance that Brian is away from the pivot point, which is 6. And if we divide both sides by 6, the force that Brian exerts is 800 newtons. Okay, and then part C says find the force that Albert exerts up on the ladder. Remember, we did on the last page, force up equals force down. So our forces up are the force that Albert provides plus the force that Brian provides, and that's got to equal our 1200. Now if we know that Brian provides 800 newtons of force, then by doing a simple subtraction we know that Albert's force is 400 newton meters. Oh, sorry, just 400 newtons, because it's not a torque, it's a force. Sorry. So 400 newtons. So Brian's exerting twice as much force as Albert. Now that would make sense because he is closer in. He's not as far away from the center of the ladder, so that's why that is true. Okay.